So this is a recording of the Affinification presentation, which was presented at EG26. I like to keep online versions of these to allow people who missed the conference to see the content of it. Much of the code for this paper was written during the annual Belair's workshop, a week-long research retreat organized by Polcry, where participants discuss open problems and prototype new ideas. It was remarkably productive, and I highly recommend it if you ever get invited. Here you can see the list of authors, including myself, who is presenting. In classical FEM simulations, we often have many tiny elements to simulate. These make the animations quite expensive, having to compute deformation of all these elements. And it's also redundant, as neighboring elements tend to behave the same, well, more or less. We have potentially big chunks deforming in similar ways. There's an opportunity to target and optimize these regions. In a way, this is what previous work did. For instance, there are sleeping methods that will remove degrees of freedom when model stops moving in the reference frame. There's also coarsening or subspace methods that attempt to reduce the level of details for some of the regions to cheaply capture the main deformations. And then there are methods that try to merge and unmerge elements adaptively to target important regions in the scene. This was the point of some of the work in my PhD thesis. We would adaptively merge elements in regions of low strain rate through a rigid body representation. Rigid bodies have low number of degrees of freedom, therefore turning many elastic elements into a few rigid chunks lead to potentially exponential gains in performance. However, rigidification has a few limitations. First, the approximation will cause the simulation to lose information about the small deformation below rigidification thresholds. It would be good to instead accumulate these in a more generalized framework. It will also miss some opportunities to coarsen regions with similar deformations, as rigid bodies are limited in their scope. Likewise, strain rates are not enough to identify which region behave the same. Because it is a dimensionless measure of deformation, we have no information about the actual directions of motions. And so maybe there's a better representation for the coarse regions than just plain rigid bodies. Affine body dynamics came out at pretty much the same time as my rigidification work. Actually, I think it was a presentation directly after mine at SIGGRAPH. In their work, they let rigid bodies deform a little through affine transforms. So instead of containing a rotation vector in a center of mass position, they encode the 3x3 deformation matrix for shear scaling and rotations, as well as a position vector. This is already linear, so it trivialized the continuous collision detection. And that's what they use their work for. In their work, they consider an energy that pretty much penalizes any deformation. So let's combine both. First, we replace the stiff orthogonality constraint with standard energies for the elastic elements. We then use a mapping matrix to lump the elements with their respective energy into an affine system. We tested various models like Sandvin and Kirchhoff, Neo-Hookean, corotational, and obviously they all work well. We also generalized the coarsening measure and clustering to affinely deforming regions rather than low strain rate regions to capture more elements for the same overhead cost. Our measure of affine deformation is particularly simple. Let's define the standard deformation gradient as f equals bx, where b is a kinematic mapping. The deformation rates can be computed with the same matrix but with velocities instead of positions. This is useful here because, unlike strain rates, we have access to orientations of active deformation with respect to the world frame. And this is also an affine transformation matrix, which is even better. Plus, it is slightly cheaper to compute than strain rates because you would need this measure to compute the strain rates anyway. With our measure in hand, we can start to cluster elements together. We opted for a greedy clustering algorithm. When an element's deformation rate is close to a center of deformation rate bounds, for a neighboring cluster, we add the element to it. This is done with the norm of the difference between the matrices. We will have a different threshold for affinification and elastification. We'll come back to it later. The f dot center is computed using the min-max bounds of existing elements in the cluster. We simply define it as the center between these two. We then update the bounds on merge as needed. Once we know the clusters, we have to generate the mapping from the full space to the reduced space. We define this mapping G with two parts. One that selects the adequate elastic degrees of freedom and one that maps the coarsened vertices to the affine bodies. Each submatrix of gamma maps to a single affine body. The upper part maps the position of the center of deformation, and the second part handles the 9 affine degrees of freedom. It also considers the distance vector Ri to the center and flattens the degrees of freedom in a vector. Great, so we have our mapping. Now all we need is to solve the reduced system. First, we do a weighted least square projection to best preserve momentum. Because we lose degrees of freedom, there are some velocities inside of the affine chunks that cannot be represented. We make sure to keep those projection discrepancies aside for later. We then solve the reduced linearized system for the change in velocities. Note that here, among other things, A contains the stiffness matrix with all of the elastic elements, so any standard elastic energy gets properly mapped to the affine space. Once we have the resultant affine space, we map it back to full space, inject the discrepancy back into the system, not to lose the small elastic vibrations. The affinified chunks are not simulated as accurately as the full space elements. As such, they lose some of the important information needed to determine whether they should remain affine or not. We predict the deformation using a cheap linear oracle. It is a single iteration of a precondition conjugate gradient with a Laplacian-based preconditioner for diffusion. For previously existing contacts, we reuse the values from the previous time steps that will also be applied as a warm start for the actual solve. For new contacts, we approximate them with bilateral constraints that are cheap to compute. See how the regions of elastification properly adapt to impact magnitude. The oracle produces an approximate change in velocities, which we can use to compute f dot. This is then used to determine when we want to turn elements elastic again. Because this is an approximation, we use a different and higher threshold for elastification to account for the approximation error. There is a correlation between error and thresholds. Obviously, higher thresholds mean more error but faster simulations. We have multiple error measures here, they're all detailed in the paper. It doesn't really matter which one you look at, they are more or less showing the same effect. The number of clusters also has a minimal impact on speed, only leaving a little shadow of an effect on the simulation time. It's barely visible. But what is interesting is that we see a sweet spot in the thresholds between 1e-6 and 1e-4. This is where simulation time greatly reduces while the error remains decently low. Most of our thresholds are in that range for the different scenes and the benchmarks. This works decently with heterogeneous materials as seen here. The toothbrush has a plastic handle and soft bristles. Note that when parts are lumped in the same affine body, it can lead to temporary stiffening of the coarsened chunks. However, what tends to naturally happen is that a small elastic layer forms itself near the boundaries of materials, allowing free motions of diverging parts. Because the algorithm for clustering is greedy and because the bounds are shifting, picking a good seed can impact the results. We tested temporarily consistent seeds and realized that while visually appealing, they may create bad clusters that persist through time. This is what we see here. On the other hand, random seeding may pick a bad initial element for a step, but recover the next one, which leads to overall better performance. Stiffness impacts affinification. For instance, nonlinearity is introduced in soft rotating beams. Highly stiff models have low deformation rate, they naturally become affine quickly. Sections undergoing similar motions like the tip of each beam remain mostly coarsened throughout the tests. Our algorithm scales quite well. Here we tested the beam scene with discretization that goes up to over 500,000 elements. Small elements tend to deform linearly. This generates more opportunities for coarsening. We have potentially unbounded improvements in performance. Consider the exponential complexity of elastic soles, and many degrees of freedom being reduced to a constant number. We kept the same Young modulus and Poisson ratio, as well as the same threshold across the beams for this benchmark. The benchmark here underestimates performance because models with smaller elements become softer, as we've seen in the last slide. We also implemented a method that optionally allows resource limiting. Unlike rigidification, it is possible without major artifacts. You start by setting a minimum percentage of coarsening, then find elements with the smallest f-dot difference with their neighbors. This can be done cheaply and quickly with an unordered case modulus algorithm, which has a linear average complexity. Then we cluster these elements with the rest of what should become affine. Regardless of whether we use resource limiting or not, our coarsened chunks have slightly more degrees of freedom than rigidification per region. However, they are much more consistent, bigger, and can accumulate some deformation like a slow crawl over time, unlike rigidification that would lose it all. See how the affinification line here is almost flat compared to rigidification. The main limitations of these methods are the same as rigidification. We have to do some level of threshold tuning. It's not that much, but it's still an extra step. It is also an approximation rather than a fully accurate solve. However, I do have another paper that does just that, and it's fully compatible, so make of it what you will. Finally, this method is subject to numerical damping, unlike rigidification that could have an endlessly spinning box in space. With this method, it will eventually stop. The current preconditioner becomes less useful as the models get large deformations. It would be a potential fix to modulate thresholds with deformation to more aggressively coarsen these regions. And finally, I don't have a GPU implementation, however I believe it is possible and I will definitely want to look into it.